Hey everyone, it's Alvaro Fuentes for the Stata YouTube channel, and in this video we would like to give you an introduction to the hdidregress and xthdidregress commands for fitting heterogeneous difference in differences models. If you're not very familiar with DID methods in general, you may want to first have a look at our introductory video on DID estimation under homogeneity. Now let's get started. In our introduction video for the homogeneous difference in differences commands hdidregress and xthdidregress, we talked about the possibility of having data for multiple time points before and after an intervention. We also pointed out that the treatment effects at each time point can be different, but that the homogeneous DID commands assume this type of heterogeneity is not present. We also talked about cohorts, or different groups that experience the intervention at different times, which opens the possibility of having cohort heterogeneity, meaning that the treatment effect is different for different groups at one particular point in time. In summary, with multiple time points and multiple cohorts, we can think about the treatment effects at one particular time point for different cohorts, and we can think about the treatment effects for one particular cohort over different time points. And in Stata, the heterogeneous difference in differences methods for this kind of analysis are implemented in the hdidregress command for repeated cross-sections and in the xthdidregress command for panel data. We'll begin by opening the file akc.dta, which is a fictional dataset of dog breeds. We have a total of 141 dog breeds, like the Chihuahua, the Chow Chow, or the Collie, and for each of these breeds, we have 10 observations, from the year 2031 to the year 2040. Notice that each year we have observations for the same 141 breeds, so this is a panel dataset where the ID variable is breed and the time variable is year. For each of these dog breeds, the binary variable movie tells us whether a dog from that breed appeared as a protagonist in a movie at some point during the 10 years we observe. For the Collie, for example, we see there were no Collie movie stars until the year 2036, so the variable movie is equal to 0 in the years before that and equal to 1 starting in 2036. In other words, the Collie belongs to the cohort of dog breeds that first appear in movies in the year 2036. Then we have the registered variable, which tells us how many new dogs of a particular breed were registered with the American Kennel Club in a particular year. In 2031, for example, 1,160 collies were newly registered. The question we have is whether seeing a dog in a movie makes people want to have a similar dog as a pet, and so we're interested in the causal effect of the variable movie on the variable registered. In estimating this causal effect, we're also going to control for the binary variable best, which tells us whether a dog breed was recently named Best in Show at the Westminster Kennel Club, like the Bulldog here, or not, like the Bull Mastiff. To estimate the causal effect, we go to Statistics, Causal Inference Treatment Effects, Continuous Outcomes, and then under Heterogeneous DID, we have 4 options for panel data. We can fit a model for the outcome with either the two-way fixed effects estimator or the regression adjustment estimator. We can fit a model for the treatment with the inverse probability weighing estimator, or we can fit models for both the outcome and the treatment using the augmented inverse probability weighing estimator. If you're not familiar with regression adjustment, inverse probability weighing, or augmented inverse probability weighing, you can learn about them in our video series on the TFX command, or you can learn about all of these estimators in the Stata documentation for heterogeneous difference in differences estimation. For our example, we'll choose the two-way fixed effects estimator under panel data, which opens the dialog box for the xthdidregress command. And the first thing we'll do is click on the panel settings button to open the dialog box for the xtset command, where we can let Stata know the structure of our panel. Remember, we said breed is our panel ID variable and year is our time variable. We click OK, and Stata tells us in the results window that we're ready to work with this panel dataset. Back in the dialog box for our estimator, we will select registered as the outcome variable, movie as the treatment variable, and we will add best to the list of covariates. Then our groups are the different breeds, and under options, we have a drop-down menu to select whether we want to model the heterogeneity over time, over cohorts, or over both. We'll set it to both and click submit. The command Stata issued is xthdidregress with the two-way fixed effects estimator. Then we have a parenthesis with the outcome variable and any covariates we want to control for, another parenthesis with the treatment variable, and finally, after the comma, we have the group option, which tells Stata the intervention happens at the level of the breeds and there is no further grouping or clustering in this dataset. Next, we have a note, where Stata tells us it created the variable did cohort. For breeds that never appear in a movie, this variable is equal to 0 or never treated, and for breeds that do eventually appear in a movie, it's equal to their cohort year. Then we have a table with more information about the cohorts, of which we have 4. Breeds that never start in a movie during those 10 years, breeds that first appear in a movie in 2034, in 2036, and in 2037. And finally, we have the coefficients table. On the header, we can see the type of estimation we just ran, and on the table itself, we have a total of 16 average treatment effects on the treated, split by cohort and year. The ATET on the first row, for example, tells us that the causal effect for the 2034 cohort in the year 2034 is about 469 registrations. In other words, if the dog breeds that first start in a movie in 2034 had instead never started in a movie, then 469 fewer dogs of those breeds would have been registered in the year 2034. This is called the impact effect because it's the effect from the same year this cohort was first treated. Below the impact effect, we see the effect of the treatment on this cohort for each of the remaining years. And for each of these estimated causal effects, Stata also reports a standard error, a t-test for the null hypothesis that the effect is 0 in the population, and a 95% confidence interval. For a quick look at how these treatment effects evolved over time, we can easily plot them using the estatat command. On these plots, we can see that for all 3 cohorts, the effect on registrations grew more and more in the years after these breeds appeared in a movie. And for a summarized look at a particular year or a particular cohort, we can use the estattaggregation command. With the cohort option, it averages the treatment effects over time for each cohort. So, for example, we can see that for the 2037 cohort, the average effect over the years 2037, 2038, 2039, and 2040 was about 2,311 registrations. With the time option, we average the treatment effects over cohorts for each time period. So for example, in the year 2036, the average effect over all the cohorts that had already been treated by the year 2036 was about 1,206 registrations. And finally, with the dynamic option, we can see what the effect is on impact on average, what the effect is after 1 period on average, after 2 periods on average, and so on. And if we want to plot the so-called duration of exposure effects, or any other aggregation, we can simply add the graph option to our command. For more information about these and other post-estimation tools for DID methods, you can always type help xthdidregress or hdidregress post-estimation into the command window. And for even more details and worked examples, you can click on View Complete PDF Manual Entry. We hope this was helpful, and thanks for stopping by.